For my demo experiment, I electroplated a metal ring with copper. The first thing I had to do in order to electroplate the ring was make a copper nitrate solution. First, I calculated the number of grams I needed to make a certain volume of solution of a certain molarity. I wanted a 1 molar solution of copper nitrate. The molar mass given on the bottle of copper nitrate I was using was 241.6 grams per mole. I wanted 500 milliliters, or 0.5 liters of solution, so using the fact that molarity equals moles over liters, I plugged in my values for desired molarity and volume to solve for the number of moles I needed. I then converted this number to grams using the molar mass. To make the solution, I measured out 20.8 grams of copper nitrate powder, put it into a 0.5 liter volumetric flask, and added water, swirling until I had half of a liter of solution. Now, before I show my experiment, I will explain how it works. Oxidation reduction, or redox reactions, happen when a reaction involves an exchanging of electrons. A compound is oxidized when it loses electrons, and a compound is reduced when it gains electrons. In a redox reaction, there is always an element or compound getting oxidized and one getting reduced. An electrochemical cell is a device that takes advantage of this movement of electrons to create electricity. In an electrochemical cell, there are two half reactions: the oxidation half reaction, where a compound loses electrons during the reaction, and the reduction half reaction, where a compound gains electrons. Generally, the oxidation half reaction involves a metal losing one or more electrons and becoming a soluble ion. The reduction half reaction generally involves a dissolved metal ion gaining electrons and becoming a solid metal. The solid metal in the oxidation half reaction is called the anode, and the solid metal in the reduction half reaction is called the cathode. These two reactions happen separately, and connecting these two reactions is a wire. When the oxidation reaction happens and an electron is lost, the electron travels through the wire to the reduction half reaction, where that electron is then gained by the reduced compound. There is also a salt bridge containing ions, which completes the circuit. If both half reactions are spontaneous, the electrons will flow through the wire on their own and create electricity that could be used to light up a light bulb. Sometimes, however, the two half reactions are not spontaneous. In an electrolytic cell, a battery is used to drive two non-spontaneous half reactions. In this redox reaction, the electrons would not flow from the anode to the cathode on their own, so the battery drives the electrons to move. The anode would be connected to the positive terminal of the battery and the cathode to the negative terminal of the battery. So, as electrons are pulled into the positive terminal and pushed out of the negative terminal, the battery moves the electrons from the anode to the cathode, forcing the oxidation and reduction reactions to happen. The same principles used in creating an electrolytic cell can be used in a process called electroplating. When an object is electroplated, the reduction of dissolved metal ions into solid metal is driven by a battery in such a way that the metal coats the surface of the object you want electroplated. In my demo, I covered a metal ring with copper using an electroplating reaction. To set up an electroplating reaction, you fill a large container with a solution containing the ions of the metal you want to plate your object with. I used the 1 molar copper nitrate solution that I made before, because I wanted to plate my ring with copper. I then took a 9-volt battery and attached a piece of copper foil to the positive terminal of the battery and the ring to the negative terminal of the battery. I then put both the copper electrode and the ring into the copper nitrate solution. The battery caused the electrons to flow from the copper foil into the positive end of the battery and out of the negative end of the battery back into the ring, driving the two half reactions. The copper anode was undergoing the oxidation reaction. Copper solid yields copper 2 ions plus 2 electrons. The ions in the solution were undergoing the reduction reaction. Copper 2 ions plus 2 electrons yields copper solid on the surface of the ring where the electrons were, causing the solid copper to form on the outside of the ring, plating the ring with solid copper. In this video, the ring is not attached to a battery and there is no copper anode. As you can see, without the battery attached, no copper is being plated onto the ring because the reduction of copper is not spontaneous on its own. Then, I put my newly copper-plated ring to good use.
Hayden, Anandi, we've been lab partners for almost a year now, and I've realized something. I want to spend the rest of my life as your lab partner. So, will you be my lab partner forever? Yes!